community and was an integral part of developing the first ever US-Chile exchange program, which is debuting this spring and summer. Dr. Cooke is also an advocate for improving accessibility in academia and was the 2020 recipient of the Inclusive Geoscience Education and Research Award from the International Association for Geoscience Diversity. We are thrilled that Dr. Cooke is our first speaker in this webinar series and hope you all enjoy her talk on the energy budget of subduction zone hazards. Without further ado, I'm going to pass along the proverbial mic, so please feel free to take it away.
Thank you very much. All right, I'm gonna share my screen and launch. You should be able to see the talk now, and you'll notice I am putting captions, also open captions at the bottom. This is the functionality that PowerPoint uses that a lot of folks don't know about. And I realize Zoom also has captions, but this also, if you are translating out of English, you can just put the Zoom window on top of the English built-in captions, and then you won't worry about blocking the slide. Anyway, I'm very excited to be here today to talk about the energy budget of subduction zone hazards. This is a project that I've been working on with Juliette Kreider, Leif Karlstrom, Krista Morrell, and Brian Unitas. And this project has started from a conversation several years ago now in the Landscapes and Seascapes Working Group. So this is really a SZ4D product in that we were talking about ways to kind of bridge silos between disciplines and really think about how processes act within a framework. And this energy budget framework seemed like a really useful way to approach investigations of subduction zone hazards. So what I'm going to share with you today is what we've come up with and give some examples from a variety of work, including some former grad students at UMass. So I'll give shout outs to them when I get to their work. All right. So the concept here is that we can think about the energy available for subduction zone hazards. So what is the energy available for landslides, for volcanic eruptions, for earthquakes? And if we have a system where the rate of energy input is greater than the rate of energy output, then we're going to be storing energy in that system. And that stored energy has the potential to be released quickly and create the subduction zone hazard. So this is kind of what we're thinking. And when we look at different hazards, we see that the size of earthquakes is measured by energy terms. And when we look at how the size of volcanic eruptions are measured, it's also with the tephra volume, which is an element of the kinetic energy of energy release. So it's sort of in line to what we're thinking about with hazards anyways. And the energy, one benefit of thinking about energy, not only can it measure hazards, but it's also a way of thinking about the various processes that occur within subduction zone that convert energy from one form to another. So here's just one example, which is that when slip happens on faults, the stored strain energy that was around the fault prior to slip gets converted into frictional heat. And on this plot of shear stress versus slip, that's the red box at the bottom, and gets converted into seismic shaking, which is this blue area that is released, and also breakdown energy, which is this energy that of how a fault stress, how shear stress evolves prior to the slip weakening distance, L. So after the slip weakening distance, you basically have sort of dynamic friction on the fault. And then looking at when we consider how stresses break down, that gives us energy that goes into propagation, that goes into damage, versus energy that goes into shaking. And this really nice experimental data on the left carefully document how that shear stress has evolved in the laboratory. So we're starting to get really nice constraints on how energy is partitioned into this breakdown energy and seismic shaking. But this is just one example. Another example is dislocation glide, which releases stored strain energy within crystals and results in a deformed crystal shape. And then the third a third benefit of thinking about energy budget is this idea of energy optimization. So when we're thinking about how systems will perform in the future, how landslides will happen in the future, how earthquakes will happen in the future, we can think about how the earth would optimize that deformation. And so an example of this on a very small scale is a deformation map, where we can see that at low temperatures, for example, pressure solution is the more optimal form of deformation within the crystal. Whereas when we go to higher temperatures, we start to get creep as the optimal deformation mechanism. And so this trade-offs between the deformation mechanisms and the manifestation of this map has to do with which mechanism is optimal at different conditions. And so going from the crystal scale to the earth, we can think of this idea as the earth is lazy and deforms in the most efficient way possible and releases heat in the most efficient way possible and it transports sediment in the most efficient way possible. So that's kind of another sort of way of thinking about the energy budget. All right, I need to define my energy terms because we use energy in a lot of different ways. And so in this case, for this perspective, we're really looking at processes that are happening in the upper crust. And so we're not going to be considering the chemistry and the thermodynamics. That is a drawback of the budget as we formulated it, and certainly room for others to come in after us and include the very cool thermodynamics that are happening. We haven't considered electrical energy, and we've limited ourselves in this consideration. The sort of first attempt is limited to mechanical work, which is force times distance, and also heat. So what is a work term? What is an example of this? So one example of a component of the energy budget is gravitational potential energy. If you take a mass and lift it against gravity, you're doing work, you're adding to that gravitational potential energy, which then would be released as that material moves down. So as sediments are transported in a river system, you release gravitational potential energy. And so one way of looking at gravitational potential energy is to look at the cumulative energy. How much energy is in the system? And to do that, you might, for example, choose a volume integral over a volume of interest. That volume of interest could be an entire subduction zone. It could be one hill slope. It could be a smaller or larger scale. The scale of the volume depends on the question you're interested in. And then you would look at the mass and the uplift to get at that potential energy. There are other ways of looking at energy that also provide interesting insights, which are the rate of energy. So we can think about if you've got some long-term uplift rate. We're looking at interseismic uplift rate in the forearc, for example. That could be a rate of energy. We could think about how rates of different energy terms are changing. And we can also look at the change in energy between two time periods. So, for example, if we have a landslide, we might look at the change in gravitational potential prior to the landslide and after the landslide and look at where the changes in energy are going in the system. So it's really pretty open-ended and lends itself to a variety of kinds of questions, a variety of scales of questions, not just spatial scale, but also temporal scale. Because you could look at change in energy over seconds, or you could look at rates of energy over thousands of years or longer. Okay, so that sort of summarizes my introduction to the talk. And the rest of the talk is really in three parts. The first part, I'm gonna kind of run through a very simple, very idealized elastic earthquake cycle energy budget, which maybe this idea has been around and may be familiar to many of you. And then we're gonna say, okay, but we know that there's more going on in subduction zones than an elastic crust that releases energy in earthquakes. So the second part, it explores that more richly for subduction zone hazards. And then the third part is lazy earth. That's when I'll unpack a little bit more things that we've learned from thinking about work optimization. before concluding. Okay, so we're considering the upper crust. And when we look at sort of a generic system with an elastic energy budget across earthquake cycles, we can start to pick out some different energy terms and some inputs and some outputs. So in this case, inputs would be tectonic work. In this particular cartoon, it's drawn with a horizontal arrow. It doesn't have to be horizontal. It can be dipping. It can be transpressional. It can be 3D. This is really just representative of tectonics. So we have, but that's the input. That's what's driving the elastic energy budget across earthquake cycles. And then in terms of outputs, there are two kinds of outputs. There's dissipative output. These are energy output that are lost to the system. You're not going to get that energy back. And conservative outputs, on the other hand, energy is actually stored in the system and can be used to drive other processes. So examples of dissipative outputs would be tsunami wave energy. Once that tsunami has happened, that wave energy has passed, it's been dissipated, and so we don't get that back. Another example of dissipative outputs would be earthquake energy, which includes seismic shaking and frictional heat. Both of those are non-conservative energy terms. And then the conservative outputs play an interesting role because if you have sort of tectonic loading of an area, you can have increase in gravitational potential in the system, and that's a way of storing energy that then can be released in other ways, released in landslides, sediment transport, or released in earthquakes. And likewise, we have internal deformation. So this is the strain energy within the, as we formulated it here, upper crust, but can be a variety of scales. And that's another form of stored energy. And in the next few slides, I'm going to use the assumption that our crust is elastic, so all that internal energy gets expended. We'll see. And so to look at an example to make this a little less abstract, we have sort of the classic subduction zone earthquake cycle with a locked interseismic period that accumulates uplift in the core arc, followed by intermittent rupture that then has subsidence. And so we can think about in the interseismic period with this uplift in the fore arc, we are storing energy as both gravitational potential energy and also shortening in the upper crust due to the interseismic locked and everything shortening during that period. And then during the rupture event, that stored internal work and gravitational potential are released. All right, so let's take a look at some scenarios of what this could look like if we start to try to partition it out. And I'll preface this and I'll repeat myself many times. This is purely schematic because there's still a lot of question marks of what the right values are. So nothing here is to scale. There are no units on here either, you'll notice. But in formulating this, we can think about energy inputs. For this very simple system, we just have tectonic work constant in time. And then the lower plot shows how that energy could get partitioned into conservative and dissipative terms. And the thick black line divides the dissipative terms, which are above, and the conservative terms, which are below the thick black line. And so we can think, for example, if there's a megathrust earthquake happening before in the interseismic period, before the megathrust events, we have increases in gravitational potential energy in green, internal stored energy in brown. And during the megathrust event, we have a stress drop, we have a release of that energy, and that energy that's released from storage then goes into tsunami energy and shaking energy that's lost to the system. Then we might, at a later time, have an upper crustal earthquake. That upper crustal earthquake does not create a tsunami, so you see there's no change in the cumulative amount of tsunami energy released, but there is an increase in the earthquake shaking, earthquake energy, which is, in this case, is shaking, frictional heat, and breakdown energy. The upper crust has an increase in that. And so we can conceptualize how earthquake events can change the budget with time. Once again, question mark, because this is not to scale. But it's sort of having this framework then gives us questions, lots of questions we can ask of what are the values of these, how should these be drawn in order to figure out how much potential energy is in the system to drive earthquakes. So one way we can start to answer that is to look at laboratory experiments. So this animation at the bottom of the slide is an experiment that was run at the University of Cergy outside Paris in sand. This is looking just at the accretionary part of the subduction zone. And we ran this experiment to look at the succession of faults that grow in the system. What's really cool about the setup in Cergy is they have force gauges on the moving wall. So while they're tracking the complex deformation in the system, they're also tracking force. So why go to the lab? It's not the same as the crust, but we can document the heck out of out of the deformation, and we know the boundary conditions and we know the material. So it gives us a nice way to test ideas and test ways of analysis. So the chart here, which is from former UMass student Justin Herbert's work, shows you the evolution of that force curve with fault growth. So we see drops in force each time there's a new fault growing, which is this idea of the stored energy being released when the new faults grow. And so we can even see similarities between the shape of the force curve going up and down cyclically with new fault growth and our conceptualization of how the stored energy in the system changes with different earthquakes. We can also try to get a handle on the budget within the system. So this is work from another former student, Jess McBeck, where she said, okay, another set of experiments run in the same lab in Paris. And here she said, okay, why don't I take the detailed displacement field coming from the experiments and take what I know about sand rheology to make some inferences on stress. And then I've got displacement and stress, and I've got all the ingredients that I need to look at work. So in this study, Jess looked at how work changes in the system with this first growth of the forethrust backthrust. So really just, she tracked, the experiments have a lot of rich data in it, but she's just looking at this first part in this study. And basically tracks how the different work components sum. And because the color scheme is different than what I've introduced so far, I put some overlays so that it's consistent colors with what I've used before. And so in the experiment, the bulk of the work is really being done by frictional heat and internal work, and a much smaller component is the gravitational work. There's some uncertainty in here, and our budget didn't exactly match. You could read the paper for a discussion of that. But what this provides then is a glimpse into, maybe we can start to think about how these work terms would partition in a subduction system. So what Jess did after this study was said, okay, well, to do that, we need numerical models. So she ran numerical models of the lab and numerical models of the crust to see how the scaling was different in the two. So what she found is that the two parameters that were very important to consider were, how does the stiffness scale from the lab to the crust? Now, because the laboratory experiments are scaled to capture the physics, that stiffness scales with length scale. So that was pretty straightforward. The bigger question was, how does the weakening distance scale, that distance over which the shear stress goes to the dynamic sliding friction? And we don't have enough information to know for sure how it scaled, but she decided to move forward with assuming that slip weakening distance from the lab to the crust also scaled with length scale. And what she found is, if it does, then the work budget in the lab is very similar to the work budget in the crust. So laboratory is on the bottom left, crust is in the bottom middle, and what you're seeing are but bar charts. The left set is for before there's any faulting in the system, and the right set is after there's faulting. So we see, for example, before faulting in the lab, a lot of internal work. And then after the faults grow, there's less internal work and greater frictional heating. And very similar results in the models that were run at the crustal scale. So insight that we can get from both lab and numerical models can start to tell us a little bit about how energy budget could work in the crust. Now, all of that was very idealized, elastic, only earthquake cycles. The crust, the subduction zones are much more complicated than that. And so we decided to include a lot of upper crustal processes into our subduction zone energy budget. You can see we've got landslides, we've got heat transport and eruptions in our volcanic arc. And then our energy budget equation or formula ends up being a little more complicated, but we still have the same three kinds of components. On the left, we have energy input. Now tectonic work is joined by heat and material input. We still have our conservative stored terms of gravitational potential and internal strain energy. And where it starts to get really exciting now are the various energy sinks that are in the system. This first one, what we're calling EDEF, is energy of deformation of inelastic deformation. So we're going to acknowledge that the crust is not purely elastic, and there is some inelastic stored energy. Anyone who's looked at outcrops in the forearc knows these rocks are deformed and they're not bouncing back. So this is an important term to have in our budget. We have ELS, energy of landslide, but this includes more broadly sediment transport as well, and tsunami, frictional heat, and seismic shaking you've seen before. And then we have this large term of volcanic energy, which includes energy of mass and heat transport through the magma transport system, as well as eruptive energy. There's, for both EV and ELS, there are a lot of processes being incorporated in a single term. And it would be really interesting for future studies to kind of break that out and look at how, for example, sediment transport, for example, produces heat as sediments are moved down a river system. All right. But this is how we sort of kept everything to the first order. And in fact, in subsequent slides, all three of these earthquake terms will all be lumped into one term. So, so let's unpack the inputs to the system a little bit. We now have heat and material mass that can input to the system. And so we divided that into radiogenic heat, which might be constant in time, but also upwelling of heat from the lower crust. And in this cartoon, we hypothesized that there could be a pulse of heat, so that this heat from the lower crust may not be constant in time. We also have potential upwelling of material from the lower crust. That's the U sub L. And then at the very top is precipitation mass. So we're thinking not just of the upper crust get new material from below, but the crust also gets material from the atmosphere. This could be glacial loading. This could be large storm events with precipitation added to the crust. So, and once again, I'm not pretending this is to scale. There's no numbers on here. This is completely a cartoon. But for example, we have a large storm here. We have a large increase in precipitation that gives us more energy for processes like sediment transport. All right, yeah, there's my question mark again to emphasize that this is purely make-believe. It's just a conceptual framework. And now we can think about, okay, there's all this energy. That's the energy input. Now this energy is going to get output and distributed by all the subduction zone processes. So once again, there's going to be conservative and non-conservative energy. So the conservative energy are the gravitational potential and the internal work, internal stored energy that can be used for other processes, and the dissipative terms are going to be lost to the system. What's different now is we've included an inelastic component. So we're going to relax the assumption that all the internal stored energy is available for other processes. We're going to say some of the stored energy is going to get locked into the rock as inelastic deformation. This is where understanding chemistry and metamorphism and mineral changes and all that could be really helpful to kind of pin that down in the future. But right now, we're just keeping it super simple. There's inelastic deformation in the crust, and we're going to take that out of the energy budget. Okay, so let's walk through a couple events and see how they impact the budget. So our first event in our hypothetical cartoon is a landslide. It's a storm-triggered landslide. There was energy input to the system and precipitation. And what we see is during this period, there's inelastic deformation that's just increasing. Internal stored work is increasing at a steady rate before and after that event, but we see a step change in the gravitational potential energies. So the idea is we've got a big landslide that's triggered by the storm event. There's increased precipitation, giving more energy to the system. A big landslide happens, and then the gravitational potential energy is locked, and that decrease in potential energy goes into the increase in sediment transport. The volcanic energy is a little hard to see in there, but it's meant to be just constant with time. So there is always some volcanic energy being released. That would be, say, like hydrothermal activity between eruption. That's just sort of a flux of heat out of the arc. So we're considering that there's an overall increase in volcanic energy dissipated through time with some abrupt changes when eruptions happen. Now we go to the megathrust event. And we hypothesized that with this megathrust event, there might be increased inelastic deformation in the surrounding rock. There's a decrease of internal work, decrease of potential energy, and now we've got earthquake energy released in that event. Not much, no change to volcanic energy during that time, but there is an increase in sediment transport because we might have earthquakes triggering landslides. And so because that shaking can trigger landslides and mobilize sediments, we have a uptick in the landslide energy released. Then in this cartoon, we threw in another landslide, and then we get a volcanic eruption. So when the volcanic eruption happens, we hypothesize that there's an increase in inelastic work. We're thinking like what's happening in where the magma was stored. There's going to be a lot of inelastic work around that storage area, decrease in stored energy, decrease in potential work. There might be a change in earthquakes. That's also possible, but certainly what's most dramatic is a big change in the volcanic energy release, because now we have heat flux during the event, as well as the kinetic energy of eruptive material. And all that eruptive material is going to get mobilized. And so there's going to be increased sediment transport. So we have a sharp increase in sediment transport with the eruption too, to acknowledge that we have this interplay of all this new volcanic material that is non-lithified and can be, or much of it is non-lithified and can be mobilized into stream networks. And then our last example is another upper crustal earthquake, which looks pretty similar to the elastic example, with the difference that now we're acknowledging that some of that stored energy is going to go into permanent damage, folding, all sorts of inelastic processes around the upper crustal earthquake. Okay, so I'm just gonna go back to segue. So with this hazard, I'm now going to show you an example of a study that sort of can be pitched in terms of the energy framework that also bridges the disciplinary silos. So, so that one is this study where Malatesta and all looked at the correlation. What you're seeing in this graph is the correlation of the distance from the trench to the shelf break, and also the distance from the trench to the locking depth and show a strong correlation. So what they're seeing, if I move to this cartoon of the subduction zone, is where we have the transition from the locked to the transitional and then slipped zone on the subduction interface. Very often the shelf break is directly above that area, and the shelf break is happening here where we have this change in ocean bathymetry. And what they proposed is that we have, during the interseismic period, there's relative upward movement here. We get sort of this uplift at the transition because this the interface is locked at shallower depths. We get uplift of the fore-arc, and that uplift is not all elastic that would be relieved in the next earthquake, but some of it is stored as permanent deformation. At the same time, we have wave action, and that wave action is moving sediments down, maybe changing the ice lofticity, this curve here. But the consequence of having uplift in above the locking depth and wave action gives rise to this change in the bathymetric profile. And this study was followed up in a very recent paper that just came out by Orion et al. And they, once again, this is another cartoon showing that same idea of shortening and thickening above the transition zone that lifts the shelf, and the wave action then causes that. And they, in this study, they also include some numerical models of this process. And so the diagram on the right is sort of their concluding diagram that shows how nature of coupling and shape of the surface can change how this is partitioned in space. And then the bottom one shows a conceptual diagram that's actually pretty similar to the energy budget I've been showing, because we have fluctuations in uplift, or we can think about fluctuations in work that are happening, but some of the uplift is getting locked into this interseismic. So this is very similar to the plots I just showed you, where some of that internal work is getting locked in as inelastic deformation. So this example is great because it shows how both sort of the sediment transport and the earthquake cycle can be combined in this framework, and also a nice way to show how observations can be compared with modeling to give us more insight. I'm now going to go to the lazy earth section of the talk and give you a few more examples where work optimization is at play in various subduction zone processes, and not just at the small scale. So I showed you this map before that shows how we can think about deformation mechanisms on the crystal scale, but let's talk about some examples on larger scales as well. So this first example looks at the evolution of magma transport systems. And in this sort of hypothetical, we can think about a fairly cold crust that has a fracture-dominated magma transport system. In this case, there's not a lot of heat flux. The magma is really confined to these fracture systems in the crust. And there's not a lot of viscous dissipation because the crust is still pretty cold. Excuse me, but over time, as more and more magma comes into the system, we're going to start to heat up the crust. And as we do so, we get a lot more inelastic deformation around the magma transport system, and the magma transport system starts to be less defined and localized to brittle conduits and form wider channels with partial melt and cool things. And then when we take this to an end member, we might envision not sort of discrete channels, but just like a large network of channels with lots of dissipative viscous deformation in the system. And so this chart modified from Karlstrom shows how this might look, this evolution from primitive magma transport systems to more evolved systems as several things change, as both the rate of viscous relaxation increases, so we get more inelastic deformation with the evolution of the magmatic system, and we also get greater heat flux with the evolution of the magmatic system. And so I mentioned this as an example of work optimization because the system the system, the primitive system, that's sort of where the magma transport is limited to the fractured, is limited because of the rheology of the crust. The crust is cold, the crust is stiff, and so the most efficient way to bring mass and heat up to the crust surface is through these localized pathways. When we get to the more evolved systems, there we've got a crust that's warmer, a lot more dissipation, and there the optimal way to move mass and heat through the system is not along localized channels, but along these wider interconnected systems. Another example of work optimization comes in this consideration of stream power and sediment transport. And stream power is the energy expenditure per length of river. So it's another work formulation within talking relevant to subduction zone processes. And this example talks about the competition between the energy required for transport and bedrock erosion. So considering first on the left, the transport limited system. So this is a system that has plenty of sediment, but doesn't have a lot of energy to move that sediment. And so what we're going to see then is the sediment wedge is going to increase until the slope of the surface is steep enough that we now have that tipping point, and there is enough slope to drive sediment transport, and then we start to get sediment transport and eventually might even get rock exposure and rock uplift. This figure on the bottom right is an example of a system that is transport limited with lots of accumulated sediment. On the other end member would be a detachment limited system. This is a system where there's lots of energy to erode material, but what's limiting it is the rock material, the strength of the rock itself, and there isn't enough energy to detach the rock and actually move sediment downstream, create sediment that's movable, I guess is the way to say it. So in this case, you also might need a steeper slope to reach that energy threshold, that you have enough energy in the system to actually pluck the rock away from the bedrock. And here's a picture of that detachment limited sediment system. So this is another nice example of optimization, because in both of these kinds of river systems, the sediment is moving by the conditions that are optimal, moving in the ways that are optimal for the conditions that they're in. And so, and what I also like about this example is it brings up this idea of tipping point. So work optimization often can tell us what will happen, but figuring out this tipping point, like how much energy is needed until you start shifting to sediment transport, how much energy is needed until you can start to pluck the rock from the bedrock. It really raises really interesting questions. I have another example from my own research group. This is another study from Jess McBeck. And she asked a question of, okay, in analog experiments, we know how the faults grow. What if we pretend we don't? And what if we use work optimization to predict where faults will grow? And so she took this wedge, this accretionary wedge, and in this sort of pink or salmon-y colored space, she basically just populated it with a range of faults that varied in position and varied in orientation, and asked the question of which of these faults would be most optimal to accommodate the contraction of the system. And you're seeing the results of these numerical models on the right. This is a numerical study based on an analog experiment. The horizontal axis is the position of the fault, sort of where the fault roots into the detachment. And the vertical axis is the orientation of the fault. So we're looking at forethrust orientation, and the most optimal, the forethrust that optimizes the external work is shown in the dot here, and overlain on the bottom as the thick white line in the middle. There's 5 white lines that show the uncertainty, and the middle white line is that most optimal forethrust overlaid on top of a strain map. So the more yellow colors are higher shear strain, and we can see that there's a really nice alignment of the location of the forethrust and the numerical model prediction of where this fall should grow. So this is an example where optimizing work gives us insight into what will happen next. And then the trick is, okay, how much energy do we need? When does this happen? So the optimization tells us what will happen, but not necessarily when it will happen. For that, we need to know something about the stresses and the strain and the stored energy in the system. So that's actually what I meant to say on this slide. Work optimization can tell you what will happen, but doesn't necessarily tell you when it will happen. For that, we need lots more cool science. And so I see this talk as really a talk that outlines opportunities for cool questions, right? If we want to constrain how much stored energy is in the system, we need to be taking measurements of strain. We need to be taking measurements of heat. And stress is going to be harder to get in the upper crust from observations, but we certainly need to know more about the rheology of the upper crust, and so that we can build reliable models that could tell us what the stress state is in the crust and tell us what the work budget is. So this really involved, it's very much in the spirit of SZ4D, because tackling these questions requires not just a single PI working on one aspect, but we really need integrated insight from a wide range of field, laboratory, and numerical studies. And so this is my conclusion slide. Not too bad on time. So my takeaway points are three. The first is that this energy budget of subduction zone hazards provides a framework to explore interactions between subduction zone processes that bridge disciplinary silos. And you saw that in the Malatesta and Orion study of kind of looking at how interseismic deformation combined with sediment transport gives us new insights on the formation of the shelf break. The second takeaway is this idea that energy optimization gives us a way to look at subduction zone processes and think about the hazards. So we can think about how sediment transport, volcanic eruptions, and earthquakes are optimizing the work budget in the subduction zone, and then figure out what are the critical values that we need to know to better characterize the hazard potential. And then that kind of led to the third one. This hazard forecasting can benefit from estimates of stored strain energy that drives earthquakes, eruptions, and landslides. So the optimization will tell us kind of what will happen, but we're going to need those values of the stored energy to really make progress on this question. That is my conclusion. And with that, I welcome questions.
Thank you very much, Michelle. I think we can all give a virtual round of applause for that fantastic talk. I'm noticing one question in the chat from Noel Jackson. Where does aseismic fault slip go in your energy budget?
Right. I treated slip in the most classic, simple way. And of course, we have aseismic slip and slow slip and all of those. What's interesting is aseismic slip doesn't produce ground shaking, right? So there's no stress. I mean, in its most, slow slip is different, but if we really say aseismic slip, then there's no stress drop and there's no ground shaking. In that sort of form, it would be inelastic work. So it's really interesting if it's because it's permanent strain, right? Because you're not going to unslip this aseismic slip. And so it would be part of that inelastic deformation that's happening between large earthquakes where there's a stress drop over a short amount of time. But while that question is easy to answer, when you start to get into nuances of like, okay, well, what about slow slip that does produce small stress drops? Then everything gets really complicated and really cool. So I want to emphasize, it's not that the world needs to fit into this generic, very simplified cartoon. I'm excited about the potential for this simplified cartoon to launch cool questions and investigations.
We have another question in the chat from Ruth Harris. I'm wondering about the interactions among chemical processes, fluids, etc. Also, of course, I'm thinking about big earthquakes triggering other big earthquakes and how that fits into the energy budget calculations.
Yeah, those are two really interesting questions. I'm gonna briefly address the first one and say I don't know, but also that I would love to know more about how the fluids are changing the chemistry and consuming energy and moving reactive components from one area to another to foster other chemical reactions. I think that's a really cool thing. I personally don't know enough about, but I think this framework sort of, I can see how that knowledge could really plug into this framework really well. And then the second question was about earthquakes, sort of loading other earthquakes. And I think, you know, in this schematic was a 1D kind of schematic. So we didn't really consider how spatial changes in stress and changes in stress state, but it's certainly, when we say that there's a decrease in the stored energy when an earthquake happens, that's a net decrease, right? Obviously, when an earthquake happens, there's a really, there's a complex heterogeneous pattern of strain and stress increase around that earthquake, which is why we do sometimes get triggering. Even though there's a net decrease, that doesn't mean there's a decrease everywhere in space. And so I think it doesn't necessarily conflict with what we've said here, but rather I see the earthquake triggering and also the cool phenomena of earthquake triggering volcanic eruptions, and all of that is sort of like the next pass down into looking at the processes by adding 3D and acknowledging that there's spatial variations, even if there's a net decrease in strain energy.
Thank you. I just want to be cognizant that we're getting towards the top of the hour. I see one more question in the Q&A section that I'll go ahead and read. Thanks from Joan Gomberg. Thanks for a super interesting presentation, a highly integrative way to try to understand subductions and processes. You've described many interesting and potentially significant energy sources and sinks, all of which cannot be tackled. Is there enough understanding already or a way to prioritize which are likely the most significant and thus where to focus research first?
I love that question, Joan, and you can probably answer this better than I can. So I think I would love, I'm going to not answer it. I think that's a great question. And I know that there's a rheology and stress workshop happening in SZ4D next week with experts on various aspects of subduction zones. I'd love to know what they think about that question. I would love to know, because they have much deeper knowledge into the particular aspects. So I am going to very not so subtly deflect answering that question and just say, I want to know what other folks think. And we do have an opportunity next week to maybe pose those questions.
Our next question is maybe better directed towards Anaïs. Can you perhaps, or can you review the SZ4D mechanisms or platforms for people working on parts of this large, parts of this large framework to communicate? And that is from Betsy Madden.
Yes, sure. Hi, Betsy, and hi, everyone. Thanks, Michelle, for this wonderful presentation. We're just in the middle of developing platforms to catalyze and foster communication collaboration among our SZ4D community and beyond. We're always very happy to receive feedback from our community, our users. So feel free to email us, or our email, can Juliette maybe write our email into the chat if you have a specific idea. I would love to hear from you. But stay tuned. We are going to talk about this more in our e-newsletter that will be distributed in June. So keep an eye for our communication about that. Thanks again for your question.
Thank you. And then we have one more question for Michelle from Pablo Ampuero. Can the energy balance approach distinguish between static and dynamic interactions, such as seismically triggered landslides versus slower forms of erosion?
I think it does. I mean, that gets to the question of tipping points again, right? Because when we have, say, like a earthquake triggered landslide, it's really clear where the energy is available because we have the stress drop, we have the change in gravitational potential, and stored energy that can then go to the landslide. So that's more clear. The sort of static triggering gets at, well, if there's something changing in time, is it that maybe there's a precipitation event, but let's take that out of it. Let's just say the hill slope is steepening over time until it reaches a point where the potential energy is enough to trigger the landslide. So I think for understanding those static events, it's really important to understand what are the critical thresholds of stored energy before the sediment transport, for example, would happen. But the framework allows for that consideration. We just need to know what the tipping point is.
Thank you. And I think for our truly last question, as we're getting to the top of the hour, from Meredith Craner, the process behind determining seismic hazard has pretty much stayed stagnant over the past decade. How do you foresee or envision knowing the energy budget aligning with pushing seismic hazard of subduction zones forward?
And this is definitely a tricky question. I think the framework itself doesn't get us forward, but perhaps illustrates a problem of if we can know how much energy is stored in the system, it might set us up better as another way to look at forecasting. But I'm hesitant. It's not that this framework itself gets us closer to that ideal of having effective ways to communicate risk to the public that's easily understood and all that. But I do think that there can be more work done, especially partnering with social scientists to look at not just how we assess risk, how we assess hazard and risk, but also how our messages are perceived by the public. I think that's a huge area where we can make a lot of strides. It might not feel like progress in predicting earthquakes, but it's hugely impactful in terms of how community members will be resilient in future earthquakes.
Thank you so much. I want to thank you again for that fantastic talk. I also want to encourage all the attendees, if you have questions after this talk, to email the email in the chat, and we will happily forward your questions along. Thank you again, Michele, for taking the time to present and be this first international webinar speaker, and we are so excited for all of this going forward. Thank you all for taking time out of your day to attend, and as a reminder, this talk will be on YouTube if you want to share it going forward. Thank you all, and have a great rest of your day.